Welcome back, and today's lesson is a little conceptual, maybe a little bit theoretical, um, really related to some language and some reasons why things occur, which is really what one of the purposes of science sometimes is, to try to understand why. So in today's goals, specifically, there are some key terms. All of today's lesson relates to the idea of something called covalent bonding. And covalent bonds are what we call intramolecular forces, the attractive force that holds atoms together to make a chemical substance like H2O. The H's and O's are held together by intramolecular forces. So the key terms in today's lesson goals, adhesion, cohesion, hydrophobic, hydrophilic, they all relate to chemical substances. I'd like you to have an idea what they mean. I'd like you to have an idea, once again, we'll quickly review how electronegativity can cause polarity. There are some other things that can cause polarity, but I want to start with the simple theoretical. I also would like to take a look at how strong attractive forces that we call IMF, not intra, inter means between molecules, not within molecules, but between them. So how strong the IMF is between chemicals. If there's attractive force, it can affect things like the state of matter, the melting point. We'll take a look at that. And then we'll wrap up with three unique properties that water has because it has polarity, and polarity creates the intermolecular force, IMF. Okay, let's get underway. So the cause of polarity, one of the causes, now there are other causes, but we're going to start with the simple, is a moderate electronegativity difference between two different elements when they join up or bond. So if we're looking at our visual here, down below, we see how we have an atom of O bonded with two atoms of H. Well, these are both nonmetal atoms, and they will undergo what we call covalent bonding by sharing valence electrons. And because O is a much stronger electronegative element, what we know is that it forms partial negative charge along the O and partial positive charge, indicated by sigma positive here, along the H. And this inheritance of poles relates to that attractive force. So since oxygen has a higher electronegativity than hydrogen, it pulls the electrons that they're sharing a little bit closer to oxygen, like you see in the visual here. And now we get some partial poles, partial negative, because the electrons live or reside closer to the oxygen than they do the hydrogen. And we end up with polarity. Polarity creates what we call IMF, intermolecular force. Now we have negative charges and positive charges along ends or positions of a molecule. And that creates attraction, similar to north and south poles of magnets. So one molecule can attract another molecule because of this. So here we show two different molecules, and these dots, dot, 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 dot. We're implying that there's attractive force or intermolecular force. Now that intermolecular force is rather weak. It's weaker than the force that holds together the H and the Cl here. That's sort of significant. If we were to think about sugar, we could take sugar, and sugar can sometimes be packed into cube form. Imagine taking a hammer and smacking that cube, right, with a hammer. What will happen is the attractive force, the intermolecular force holding the individual molecules of sugar to each other, gets weakened, and it breaks down into finer crystals. We could even break it down to what we call powdered sugar. But the molecules themselves are still held together. The C's, the H's, and the O's that hold a sugar molecule to itself are still holding those sugar molecules, keeping them sugar. So the identity is still kept by its intramolecular force, but we weaken the intermolecular forces by making a finer crystalline solid, and we get much finer crystals as a result of weakening the intermolecular force, the attractive force between individual molecules. So there's a difference between intramolecular are chemical bonds that hold the atoms together. Intermolecular forces are attractive force that would allow one molecule to attract itself to another. And if we have polarity, we have what we call intermolecular forces. And we've discussed this before, but when particles are either polar or ionic, we have some kind of intermolecular force or attractive forces that can affect properties. So what that might affect would be the state of matter. Here we got solids, liquids, gases. Well, in order for a chemical to remain a solid, like we see here, the particles have to be attracted to one another very tightly. And what does that is IMF, intermolecular force. As long as there's a relatively strong intermolecular force, it can remain in the solid state. Imagine weakening that by adding energy. If we add energy, maybe we smack it with a hammer, that's adding energy. Maybe we heat it up, that's adding energy. What can happen is that energy can weaken the intermolecular force and cause the solid to enter the liquid state. We call that melting. And by weakening the intermolecular force, we affect the state of matter. If we continue adding energy, we completely eliminate that intermolecular force, and we create what we call the gaseous state of matter. Now the particles carry so much energy, their attractiveness for each other really is not a strong attraction because they're moving so rapidly. So if we slow them down by removing some of that energy, maybe the gas turns back to a liquid. Continue slowing them down, maybe it turns back into a solid. But by slowing them down, what we're doing is we're influencing intermolecular force. So you can imagine here, if we're looking at this, here's water molecules. One water molecule attracts a different one, which attracts another one, which attracts another one, which attracts another one. That allows water molecules to stick together. It's because water molecules have intermolecular force created by polarity. So bond type, chemical bond type, affects whether or not we have intermolecular force, the attractive force between individual molecules. If it's weak, then we have very little attractive force, and maybe we have what we call gases. So gases exist because there's not much attraction between individual molecules. And what we have when we do have IMF, it can affect state of matter. Is it a solid, a liquid, or a gas? How soluble it is. Does it dissolve in another material? Melting point. In order to turn a solid back into a liquid, we need to weaken that IMF. So the relative strength of IMF has an impact on the properties of chemical substances. So there's some key terms that relate to this. So here's the key term that we would call adhesion and relating adhesion and cohesion. These are two key terms that are often misused. So here we see particles of water sticking to the blades of grass. Well, that's because water has what we call polarity. And apparently there may be some polarity on this blade, or maybe not. If there weren't polarity, the water molecules would slide off very easily. If there is some polarity, the water molecules will sort of stick to the surface. So what we can see is there's a term called cohesion. And if you look here at our little diagram, cohesion says particles of the same type stick to each other. So water molecules have nice cohesive force. That's why we can build a dome on the surface of a penny. Water molecules stick to each other rather well. They also stick to the surface of the penny rather well, and that's what we call adhesion then. So the particles stick to other types of particles. Let's take a look at adhesion and cohesion, those forces, in an interesting way here. I'm going to pause the video here so that we can access what I'd like to share with you. That is, if I can find the little tool to do that. There we go. Okay, so we're going to take a look at the properties of adhesion and cohesion in space. So remember, particles sticking to other particles, or particles sticking to the same particle, and that's what we're talking about with adhesive and cohesive forces. So let's look at what happens in the absence of gravity with adhesion and cohesion. Pretty interesting stuff here.
you get a cloth dripping wet without gravity and you wring it out, what's going to happen? What will happen to a wrung out cloth? So, and I had to use equipment that was here on board the space station. We may have the coolest washcloths ever here on the space station. I'm going to show you. Here's one of our washcloths.
I'm going to pause this and see if I can't maybe turn the volume up a little bit for you. Looks like that's not going to be possible. So we'll do our best with what we have.
And it's compacted. It's put down into this little tiny hockey puck so that it saves space. But when you open up a hockey puck and you pull out your washcloth, this is the one I'm going to use for the experiment today. And so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise somewhere. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out.
So you can see we're in space here.
Merritt and Kendra suggested that I dip this in a bag, but bags don't hold water in space. So instead, I filled a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth.
So water comes out of the bag, and what we see cohesion, water particles sticking together really, really well. So cohesive force, there it is. Beautiful cohesive force. Look at that perfect stream of water out of there because of the cohesion.
So here's a soaking wet washcloth.
Now we also see adhesion.
Get the microphone so you can hear me while I'm
So
talking.
the water is not leaving the cloth. Now we're going to wring it out.
It's really wet.
And we see adhesion, water sticking to his hands, staying stuck to the cloth. So we see both adhesive and cohesive forces, and this is because of polarity. So apparently the cloth has some polarity conditions.
The water's all over my hands. In fact, it rings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of doesn't stick to my hand.
So adhesion and cohesion, folks, there it is, evidence of it. So we'll stop that share. We will go back to where we left off. And here we go. So back to where we started. So cohesion, attraction of particles of the same type, water to water. Doesn't have to be water to water, but in this case it was. Adhesion, the attraction of particles to different types. So the terms adhesion and cohesion, pretty simple words. They relate to things sticking together. So two other words similar to this, hydrophobic. Yes, you've all heard of phobias. Phobias means fear. So when a chemical is hydrophobic, it sort of fears water, which means it does not stick to the surface, or it will not stick to water molecules. That would be because of lack of polarity, lack of attractive force or intermolecular force. So maybe on the surface of wax, water molecules make these nice dome shapes because they don't really stick to the wax surface. Wax is hydrophobic. Water on the surface of a penny, however, kind of lies down flat like you see up here on top. So hydrophilic means sort of water loving, and it will easily stick to that surface. So we see the penny, water sticking to itself, making a nice dome, and sticking to the penny, allowing it to flatten out a little bit. As opposed to hydrophobic, maybe this is the surface of wax. If you ever notice a freshly waxed car, water droplets build up in really large domes or really large beads. That's because wax is not polar in nature. It doesn't really have intermolecular force like water droplets would. So hydrophobic, hydrophilic, really just key terms that relate to water. Ability to stick to water, we would call those chemicals hydrophilic. Inability to stick to water, we would call those chemicals hydrophobic, and it relates back to our bond polarity. So water has some unique properties related to its polarity. And we're going to take a look at those three unique properties. First of all, it's what we call the universal solvent. It has something called high surface tension, and it can exhibit something called capillary action. So let's take a look at those three properties. So because water is polar, it sticks to other chemicals, specifically chemicals that need to be transported throughout the body or throughout living organisms. So sometimes there are nutrients, minerals, hormones, waste materials. If we're talking about a living being, to get those materials transported through the lungs, the blood, the skin, the muscle, the brain, the bones, we need them to be soluble. And water is sort of the vehicle that transports it around. Naturally urine is mostly water. Well, that transports these materials that are waste materials out of the body. So water being a universal solvent serves very, very important functions for living organisms. Because it's polar, it allows nutrients, minerals, hormones, and waste materials to be stuck to it and either carried away or transported to where we need them. So we have similar behavior in plants. So here we see an ion of sodium, right, because it has a charge, being stuck to water molecules. And that allows the water molecules to transport it to where we might need in the body. So we have this next concept for water called surface tension. And if we've ever noticed, there are some insects that can skim along the surface of water. We could also balance, if we're really delicate about it, we can lower a paperclip into a glass of water very delicately, and it will actually float. And it will float because water has what we call surface tension. And we'll look at that in a moment, what that sort of means. So there's sort of a barrier along the surface as the water molecules stack up. So let's take a look at just a quick segment of video that kind of describes this surface tension in a little more visual way than I can do with what I have with our slides here. So we're going to have to share that with you because I don't believe you can actually see that yet. And I think you have it now.
By 2050, there will be more plastic than fish in the ocean.
Let's skip those ads. We don't care about that.
Welcome to a Mad Scientist production of Surface Tension, in which we will look at how
intermolecular force, IMF.
Of a liquid. So what is going on at the surface of a liquid? Let's take a look by shrinking to the nanoscale. So here we are looking at the individual molecules in a liquid, and let's say that each blue circle represents a molecule of water. Due to kinetic energy, the particles that make up a liquid are in constant random motion, and so they will have a random arrangement. You might expect the particles at the surface, at the micron level, to form a random surface as shown here. But what we should find out is how do intermolecular attractions influence the surface? First, let's look at intermolecular forces under the surface, where attractions of individual molecules pull on each other in all directions. At the surface, pull on the molecules is lateral and downward. There is negligible attractions above the molecules, and so the net force on surface molecules is downward.
Paraphrase that. If we notice up here at the surface, these molecules are not attracted to other molecules above because there is no more water above. So what ends up happening is the attraction is in a downward direction because the particles are either along the same level or below it that it's being attracted to. And what that's going to cause is that's going to cause a much tighter attraction near the surface than somewhere below the surface. And it causes what we call surface tension.
The result of this downward force is that surface particles are pulled down until counterbalanced by the compression resistance of the liquid. Surface molecules are compressed more.
So if we pause this for a second, this allows us to take something rather lightweight like a paper clip and balance it along the surface here because the paper clip has difficulty overcoming this intermolecular force because it's too light. The paper clip should actually sink because it's more dense than water, but because it's so light, it won't sink till it overcomes this attractive force that we call surface tension.
Tightly together at the sort of skin on the surface with less distance between them compared to the molecules below them.
So surface tension, because the molecules up near the surface do not have any molecules above them to be attracted to, it pulls them downward and it pushes them closer together because of that downward pull. And we end up with a concept, it's called surface tension. Let us go back to where we left off. And we'll share back where we were. Okay, so here we are back at surface tension, right? Because the paper clip is stuck at the surface. The reason it's held up there is these particles up near the surface are sort of tightly attracted to one another, and the paper clip's just not heavy enough to sink downward, similar to this insect called the water strider. So it's kind of like a barrier or a skin because of polarity. Stronger intermolecular force at the surface than there would be below. And that leads us to this concept called capillary action. Some of you may have noticed if you ever dip a straw in a fluid, if that fluid is mostly water, that fluid will rise up into the straw, and that's because of adhesion and cohesion. Particles can stick to particles of the same type if they're water, and particles can stick to many different kinds of surfaces of different types, also if they're water. And what that allows to happen is that allows the fluid to be drawn up into that narrow opening, sometimes called a tube. And the more narrow that opening is, the further upward it gets drawn because there's a tighter grab onto the surface of the narrow opening surface than if it were a wider opening surface. So let us take a look at sharing this idea that I sort of explained visually here. So we'll pause this. And we got to share this with you so you can actually see it. Okay, I think you should be able to see it now. And here we go.
When a tube is put into water, adhesive forces cause the water molecules to adhere to its surface. At the same time, the cohesive forces between the water molecules cause the surface of the water to try to level out.
Okay, so adhesive forces allow the water molecules to stick to the surface of the tube, right? Cohesive forces draw more water molecules up toward those ones that are stuck to the tube, and the water rises up through the tube. And the more narrow the opening, the higher the rise would be.
This pulls the water up the tube if it is narrow enough, only stopping when the force of gravity acting on the column of water matches the pull of the capillary action. The narrower the tube is, the higher the water rises.
Okay, so that is, excuse me, that is that property that relates to the key term of capillary action. Okay, so let's just go back and revisit. Water has three unique properties, all as a result of intermolecular force created by polarity. And one of the causes of that polarity would be differences in electronegativity, ability to attract valence electrons between individual elements. So universal solvent, water is a very good solvent. It dissolves a lot of materials. That allows it to transport nutrients, wastes, hormones, or materials throughout a living organism where it needs to be, move it to a new place. It creates a concept called surface tension. So near the surface of a liquid, there's a little bit of a skin or a barrier because the particles are more tightly attracted. And it creates something called capillary action, which actually allows plants to draw their minerals up without really having to do any work. So the water from the soil, water gets stuck to the soil because water is adhesive. It adheres to soil particles. A root structure develops in a soil. That water gets drawn up into the root structure because there's an opening. Because of adhesive and cohesive forces, the root structure of plants can really absorb water or, draw water upward without really having to do any work. So that wraps up our lesson today on polarity and attractive force called IMF and how it creates some interesting things that relate to ideas in the world. So until the next time, folks, I bid you peace. And I hope you found today's lesson interesting and maybe even a little bit useful.